going to begin talking about chaos and nonlinear mechanics and chaos. So this is chapter 12 out of Taylor. In this chapter, he does a lot of calculations. He uses a lot of numerical calculations. So this is the first one that I'm actually going to be using figures from the book and projecting them on the screen because I just could not do it without that. So many systems which are nonlinear exhibit chaotic or unpredictable behavior. Now, most of what you cover in especially in undergraduate physics education, is going to focus on things that are linear and nice and well behaved, because this is what we are actually able to solve analytically. We're focusing not on the problems that exist in the world, but on the problems that we can actually solve. We're going to focus here on a damped driven pendulum. The book uses the abbreviation DPP. I personally get irritated with excessive use of abbreviations, so I'm going to try to call it the damped driven pendulum. This exhibits chaotic behavior in certain regimes. Now, we actually already covered a damped driven pendulum, but we covered it for small oscillations. And when we have only small oscillations, the behavior is not chaotic. It is actually rather predictable. But now we're going to allow larger oscillations, and we're going to see some different chaotic behavior and describe what happens when that driving force is large and when the compared to the effect of the damping. Now, there are broadly two classes of systems that can exhibit chaos. There are dissipative systems where there's energy lost. An example is a damped-driven harmonic oscillator. And then there are non-dissipative systems that exhibit chaos, and we are going to focus on the former. Dissipative systems where there's energy lost. Focusing in on the damped-driven pendulum. So we're going to start by going back to linearity and nonlinearity. Almost everything that you talk about in physics, at least that you would have seen so far, is going to somehow be a linear system. And to exhibit chaos, something has to be nonlinear. So what do we mean by linear? The classic example that we have spent a lot of time on is simple harmonic oscillation. So here it is a differential equation, but it depends only on the function and its derivatives linearly. We don't have x squared, we just have proportional to x. We have covered some nonlinear systems in this class. When we talked about air resistance, we considered the air resistance where it depends on the velocity squared, which is in fact nonlinear because it depends on x dot squared. We also, we can talk about slightly more complicated systems, so we can add a driving force, which could depend on time, but it only depends, it still only depends on x and x dot and x double dot linearly. Another example is a pendulum, and I found the book's notation here to be a little bit less than enlightening. This L, we've used it to mean angular momentum, and we've used it to mean the Lagrangian. Here, L means the length of the pendulum. So the length of the pendulum, so ml squared phi double dot equals negative mg L sine phi. Now this is, this one is not a linear equation because you now have a sine phi dependence. And here, this form is using the torque, the moment of inertia, I times the second derivative of phi is equal to the torque which is equal to the force times the moment arm. Here, the moment arm is L, and the force is negative mg sine phi. So this is an example of a nonlinear equation, and most of what we have done to date is to say it's approximately linear because I can use a small angle approximation and make it linear. Why am I making it linear? Because I know how to solve linear equations. I do not know how to solve this equation without a computer. All right, so, and now since if you took my class, you learned how to solve systems numerically last semester. As soon as you use a computer to solve it, it doesn't really matter very much if it's linear, other than telling you about how hard it is to solve and how much computation time it'll require. We have looked at mr double dot equals negative gmm over r squared r hot hat. So this is the effect of the force of gravitation. This is also nonlinear, but in this case it happened to be solvable, which led us to the equations describing the orbits of the planets. And if you change the constant and possibly the sign, you can have electromagnetic scattering because it takes the same form. In general, linear equations are solvable. Nonlinear equations are not solvable. And nonlinear equations also tend to be much more sensitive to the initial conditions. Now, the reason we're talking about this, even though it's not, it's outside of our comfort zone, is because obviously the vast majority of physics out there in the world is nonlinear, and much of it can be chaotic, has motion that is chaotic. So nonlinearity is necessary but not sufficient for chaos. And what that means is that in order to have chaos, you have to have a nonlinear equation. But if you have a nonlinear equation, that does not necessarily mean that you have chaos. So chaos requires nonlinearity, but it also requires somewhat complicated equations of motion. And we're going to defer to we're not going to worry about right now how the conditions for more complicated equations of motion are. We're going to focus on how you can treat that and how you can make sense of chaos. So an example of we've already mentioned this, but this example we're going to cover extensively in this chapter is the damped driven pendulum. It has equations of motion. This is the length, not the angular momentum. This is the damping factor. It is proportional to, so we're going to go with linear damping. So this is proportional to the, so remember, this is I, and then phi double dot. So this has the form of torque. So it is the moment arm times the force. So the force is then acting as if it were acting on the center of mass, and the velocity is L times phi dot. So the force is BL phi dot, but then since it's acting as if it is at this is the length to the center of mass, so then that is the moment arm there. Plus L F of t. So this is allowing some general force, driving force. This is chaotic. You also have chaotic motion with a double pendulum. So where you have two pendulas connected through a pivot point. We actually approached it with small angles earlier. If you do that, you can make some conclusions. So then you can ask what's special about nonlinearity. Why is it that it causes chaotic motion? Turn it on its head. It's actually linearity that is special, and it is unusual to have linearity to the extent that what we have done throughout this book and throughout your studies so far, is to take something which is not linear and we approximate it so that it is linear so that we can solve it. And be careful, because the behaviors and assumptions from linear behavior do not carry over into nonlinear behavior. We can start with the superposition principle. So the superposition principle says that the sum of solutions is a solution. This is true when you have linear equations. So let us have some differential equation, which is linear. And it's got some functions which may depend on time. Now, we're going to assume that these three functions are known. This is an equals. And then, if we have a solution, if we have two solutions, so x1 solves this equation and x2 solves this equation, then you can come up with any solution, which is a1x1 plus a2x2 will also be a solution. And the way you can show this is because, of course, as you take your derivatives, so one derivative and look for different colors, two derivatives. You would simply take the first and second derivatives by adding dots. Each of the derivatives are additive. So then when you plug it in here, you will have, you can rewrite this however you want, but you would then factor this out and you would have P of T a1x1 double dot plus a2x2 double dot plus Q of T a1x1 dot plus a2x2 dot plus R a1x1 plus a2x2, and then I can gather terms, and these guys will solve the equation and add up to 0, and these guys will solve the equation and add up to 0. So I can factor this out so that I have A1, I'm going to drop the explicit time dependence, Px1 double dot plus Qx1 dot plus Rx1, and something similar for x2. Well, now this has to equal 0 because x1 is a solution, and this has to equal 0 because x2 is a solution. So I find that if x1 and x2 are solutions, that the sum of them, that any sum of them also has to be a solution. This is not true if you have this function being nonlinear. So one of the exercises in the book is to take something and even just add a square root. Now, as soon as you add a square root, here, if I have two solutions, I can't separate these two parts, and so I cannot write this. I could write that this is equal to the negative square root of that, but I will overall not see that it is in fact a solution because I can no longer factorize the two solutions. So we cannot do what we did before and find a bunch of different solutions and say that our solution in general is a sum of the other solutions. What we're going to have to do is solve the problem numerically. So that leads us to the system that we are going to focus on for the rest of the chapter, the damped driven pendulum. So we will, again, we start with the moment of inertia, ml squared, and then we are going to multiply by the second derivative, the time derivative of the angle. And then this is the moment arm times the force. And here you can see the, and we're only looking at the force in the direction perpendicular to the pendulum bob. Here we're treating, the picture is shown as if you have a mass at the end of a massless spring, but you actually could have a physical pendulum where this is the position, the effective position of the mass. But we'll leave it as a massless string, and then here you've got the bob. You have air resistance, so if your air resistance is always going to be in the opposite of the direction of motion. So it's going to be negative b times the velocity, then mg sine phi, and then the driving force. So the mg sine phi is because you are looking at the component. So here, this is phi. So here you want the component in this direction. That is the total force is mg, and this component is mg sine phi. And then here, this is, the velocity is L phi dot, so this is negative B L phi dot. And using that, we get the equation ml squared phi double dot equals negative B L squared phi dot minus mgl sine phi plus L f of t. For the purpose of the calculations here, although sometimes the book is general and sometimes it is specific, but we are, Taylor did a whole bunch of numerical calculations, and I don't want to repeat them, and I can't repeat them in a whiteboard lecture. I would need a computer. We're going to assume a force of this form. This is the drive frequency. And this is the drive amplitude. And we can rewrite this. I am going to divide through by ml double dot and define some new variables in just a minute. So here we do the same thing that we did when we covered oscillations. I'm going to move everything that depends on phi and its derivatives on the left-hand side, and I'm going to leave the driving force on the right-hand side, and divide through by ml squared. I get phi double dot plus b over m phi dot plus G over L sine phi equals F naught over ML cosine omega t. And now I'm going to define a bunch of variables. This guy we will call 2 beta. This matches the terminology when we covered oscillations. This guy we are going to call omega naught squared because this is the natural frequency if we had small amplitude oscillations. And this we are going to call gamma omega naught squared, where gamma is now F naught over M L omega naught squared. And when we do that, we can rewrite this equation as phi double dot plus 2 beta phi dot plus omega naught squared sine phi equals gamma omega naught squared cosine omega t. Okay, so we then want to look at some of the expected features of the damped-driven pendulum. So we have some features of a linear oscillator. So when we worked in the linear region, we studied this one extensively. And what we expect is that when we deal with small oscillations, that this should reduce to our old friend, the damped-driven pendulum with small angle oscillations. So if we work in that case, this reduces to simply phi, or at least it is approximately phi. The initial behavior of the pendulum depends on the initial conditions, but any differences due to initial conditions die out rapidly, and the motion approaches an attractor. The attractor was our solution here for the damped-driven pendulum. The damped-driven pendulum will approach a solution where it oscillates with the same frequency as the drive frequency, but it has, in principle, it can have at least a phase shift. So here, I actually want to go back and revisit the solution that we had for a damped-driven harmonic oscillator when we're considering the linear limit, where you are basically assuming that you only have small oscillations and that you can approximate sine phi as simply phi. When we did that problem, we got the solution that phi of t was equal to a cosine omega t minus delta plus, the more general way of writing the solution was C1 e to the R1t plus C2 e to the R2t. And then these, in the case of weak damping, so that R is negative beta plus or minus I omega 1. So in the case of weak damping, omega 1 is greater than 0. And when that happens, then you have an exponential decay multiplied by some oscillations. So your form then takes, the solution then takes the form C1, well, actually, we're going to put the e to the minus beta out in front. E to the minus beta t C1 cosine omega 1t plus C2 sine omega 1t. So the properties of this solution are that initially, so to get the initial conditions, that would fix A, C1, and C2. Or sorry, A is fixed not by initial conditions, it is fixed by the deriving frequency, and in somewhere in chapter 5, you can look up what that is in terms of the driving frequency. C1 and C2 are set by the initial conditions, but either way, what happens if you let the system run for a while, this goes to 0, so these parts, which are what we call the homogeneous solution, go to 0, and you are left with the particular solution, the term that oscillates with the driving frequency, but possibly with a phase shift. Now, when we no longer consider this to be linear, but we allow the system to, so we're going to put in the actual sine phi, we're going to allow the pendulum to oscillate beyond what we might think is a small angle. It can get a little larger, but we are still in a region that, we still have weak damping and the driving force is not too large. Then you're going to see the system roughly behave like this. You will have some initial wiggles determined by the initial conditions, but as time goes on, you're going to approach what we call the particular solution. So you can numerically solve that, and this is shown here. And what you see actually, so this is with gamma of 0.2, R is 1, so the drive period was, tau is chosen to be 1. Actually, this book sneaks that in. It says tau equals 1, and then later on it just has 1. It's actually tau. I did in some places go back and add taus. So the period is 1 in this case, and what you see is that obviously at the beginning your drive amplitude is not what it ends up being. You have some squiggles, but even after 1 period, this system approaches its constant number of, the equilibrium that it will eventually end up at. So it doesn't take very long. It shows qualitatively the same type of behavior. Now here, 0.3 radians, is that small or large? That maximum oscillation is 17 degrees. If it goes to 0.3 radians, that means that it's oscillating 17 degrees. We more or less consider a small angle approximation to be valid within less than about 10 degrees. So this is very much not the small angle approximation has some tension at this point because theta is a little bit large, but it is not outrageously out of range. We can literally check the values of the small angle approximation there. Sine of 0.3 is equal to 0.2955. So that really is approximately 0.3, but you are starting to see differences at about the 5% level. So that's 5% different from theta. So it's a pretty good approximation. And then numerically, when you look at the actual numbers, it still looks like all of the qualitative behavior of our linear simple harmonic oscillator, it basically holds. That's what we want whenever we start doing problems. If we have one solution that is valid in a certain regime, we want the solution as we expand beyond that to simplify to what we know should be the right solution in cases that we have already solved. So we have a funny term for this particular, the particular solution. We call it an attractor. And we call it an attractor because with time, all of your solutions, whatever your initial conditions, any system is going to approach that solution. Numerically, it might be ever so slightly different from it, but as time goes on, it is going to approach this solution. So whenever you have, whatever the initial conditions, for a system like this, it approaches a unique attractor. So this is something where this is not chaotic yet. It approaches a unique attractor. Now, you can't necessarily solve it linearly. You may have to use a computer, but you can still tell me what it's going to do at t equals infinity because it approaches this solution. It approaches that independent of the initial conditions. And in this case, the attractor is sinusoidal with an angular frequency of the drive frequency. Now, we can take this solution and we can look a little bit beyond it. And we want to, if the first thing that you do when you're making an approximation and you try to solve a problem is that you take a Taylor series and you look at the lowest order solution, well, the next thing that I'm going to do is consider the next highest order solution. Sorry, not the next highest order solution, the next highest order term. So we have from the Taylor series for sine phi, this is approximately phi, but then we can take the next highest order term, which is a minus 1/6 phi to the third. So then that makes our equation, if we plug that in instead, approximately phi double dot plus 2 beta phi dot plus omega naught squared. And then this is phi minus 1/6 phi cubed equals gamma omega naught cosine omega t. So here this much, accepting our new term, everything else is solved exactly by our original solution. So the new dependence has to be canceled out if we consider this higher order term. It has to be canceled out by these terms. Because this is, if we are to solve this guy solves that. So the question is, can we consider a higher order term that is a correction? So we are going to guess that the solution is approximately. So we're going to look at what this term actually looks like approximately. So if we have a solution that looks like cosine of some number cubed, this is left as an exercise for the student, because that is what Taylor does with all sorts of ugly math. And this involves some hairy trig identities that you probably haven't thought about in my case, in several decades, and is left as problem 12.5. So this is what your solution looks like. And then we know that we have a solution which has got to be approximately this. So we are going to try adding a term which, So here, this has a 3x, and we're going to try adding a term which has a period 3 times the driving frequency and see if that works. So that would give us a term here, which could cancel out some of the other terms. And then you can substitute this, take this and put it back into the here and see what the solution looks like. And you will see that there are small corrections. And what you'll see is that the next higher order correction, so then this, because this solution is approximately this term, oh, I dropped the 3 when writing that down. This term has to be much smaller than that term. And you will see that that what you're left with here, when you plug that in, is going to be of order 3, and then you would have to consider a higher order term, which will have some frequency of multiple omega, n multiplied by an omega. So we call these the harmonics of the drive frequency, just like when we were talking about, way back in intro physics, we talked about waves on a string and we had harmonics, and the harmonics have multiples of the base frequency. These are harmonics of our original frequency, and as the drive strength is increased, as this term gets larger, the importance of the harmonics increases, and you pick up more harmonics of the drive frequency. Where the nth harmonic has a period which is 2 pi over n times the drive frequency. So the period for the third harmonic is 1/3 the original period. The period for the fourth harmonic is 1/4, and so on. So the oscillation will still have the same period, but it is going to the same overall period, but you're going to have slight distortions of the shape. So it's no longer the pure case of weak driving, as the initial transients dry out, you're still going to approach the attractor, but it's not going to be quite just this attractor. It's going to include these as well. And here what you can see is this is the numerical solution, and here you can see the difference between the numerical solution and this term overall, where the dashed line is just this term, the pure cosine of omega, and the solid line is the actual solution, so it includes this. And this is done numerically, so it's going to include higher orders as well. So you still have the same overall period, but you are getting a slightly different shape. And we were able to do this with our old friend, the Taylor series, because we take, and I've said this many times, classical, theoretical physics is taking a Taylor series, and then when that's not good enough, you take the next higher term in the Taylor series, and that's all we did. Now we're going to increase the drive strength, and I actually forgot to mention earlier, before we were dealing with drive strengths where that gamma factor was all less than 1. We are now going to move it slightly above 1. When you have a gamma less than 1, that is, so if we go back to our equation, when gamma is greater than 1, you have this term gets to be where its oscillations are larger than that term. When gamma is less than 1, this term's oscillations are less than this term. And so that is why it makes sense that this gamma is driving the how chaotic the solution is, how predictable your answers are going to be. Now here you can see the numerical values of the numerical solution to an initial, so there's specific initial conditions. I think it is pi, well, you can read off that the initial position is 0, and this is, and then gamma of 1.06. What you see is that there's actually some totally wild oscillations. What this is telling you, because this is an angle, and here you reach 2 pi, so it increases, decreases, increases, keeps going, does a full rotation, does another full rotation, swings back, and then oscillates. And it's oscillating with an amplitude that, if you read off the graph, is approximately pi. So it's doing this. And it swung and stayed a full turn further than where it started. So what's not clear from this figure alone, you have to look in more detail, is whether or not the motion is exactly periodic. You have to look at the numerical values. It turns out that this is actually periodic if you go way far out here and you compare whether or not this trough is exactly the same height as that trough and this peak is the same height as that peak. The book lists the values. I'm not going to reproduce them. And then we're going to increase gamma just a little bit further. So gamma equals 1.07. And here, again, you see wild oscillations. So you've done a full rotation, you do another rotation, you go one rotation back, one rotation that way, one rotation back, and then you actually end up with a negative. You end up having done a full rotation in the negative direction before it sort of settles down to this type of periodic motion. So a few things. Note that you are so it is, there's some, well, it's not technically chaotic, you are yet, because we don't have, because it will settle into some type of solution, but you have some somewhat, at least analytically, not predictable motion that followed by settling into some type of solution. Now, if you zoom in here numerically, what you see is that it doesn't settle into the same, this is not periodic with a period of 2, which this is, the whole system is set up so it has a period of 1, so it's not a period of the initial driving force. It actually repeats itself every 2 periods of the initial driving force. So it does almost look periodic, but it's jumping so that you have to go 2 periods to get to the initial amplitude. And this, the troughs, so the troughs oscillate between 2 different heights without stopping. It doesn't settle into to oscillating with 1 height. And this is, so we will call this period 2, where the period is twice the initial driving force. And this we call a subharmonic of the drive frequency, which is sort of the opposite of a harmonic. A harmonic is when the frequency, the angular frequency will increase, the period decreases. So if you have harmonics and you add up frequencies with a bunch of different harmonics, they have the same period as the original frequency. When you add up subharmonics, the period increases. It takes more time to repeat the motion. And we can, but here you can see the dominant behavior is still period 1. We can increase the increase gamma a little bit more, 1.077, and then you start to see this is much clearer. This has a period 3 times the original. You have to, here we go from, so to have one full cycle, we still have periodic motion, but we're going to, it takes from about 5 to 8 to go through one cycle. And this is called period 3. And then you can start to see some different behaviors. So this is the same value we have stuck with. So so the gamma is 1.077. And we start with different initial conditions. For the dashed curve, you have an initial velocity of 0, and for the and an initial position of 0, and for the solid curve, you have an initial position of pi over 2, and an initial velocity of 0. So you've changed the initial conditions, and what you see is that one of them settles into this period 3 motion, and the other settles into period 1 motion. So some motion that has the original period. And you will end up on either of these 2 different solutions depending on what your initial conditions are. And we talk about this as having 2 different attractors. So depending on your initial conditions, you can end up on this guy or this guy. And in principle, a system can actually have more different attractors. We start to see another phenomenon as we continue increasing gamma. So let me maybe even zoom this in. All right, and now you can see why I am not reproducing this. You wouldn't even if I could draw it, you probably wouldn't and shouldn't trust me to reproduce it accurately. Here we have gamma equals 1.06, so slightly above 1, where we're going to start to see some of this chaotic-ish motion, and you zoom in, and what you see is that it does indeed return to the first attractor, to the solution that has the drive frequency. You increase gamma to 1.078, and this still looks like you see, well, throughout all of these, you're still seeing that the period 1 motion is dominant, but when you zoom in, you can actually look, so zoom in and look at the troughs, and you will see that it takes 2 periods for the motion to reproduce itself. And then here, gamma of 1.081, and now you can see that actually, because this trough is not exactly the same as this trough, you have to go through 4 periods to get periodic motion. And then you increase further, 1.0826. And here, to get back to the original height that we had, you have to go through 8 periods. And this phenomenon is called a doubling cascade, where it actually, so numerically the differences are rather small. They seem to end up in roughly the same place, but there are qualitative differences. There are quantitative differences where you're not actually getting back to period 1 motion. You're doubling the period. And this period doubling is observed in many different cases, such as voltage in electric circuits and flow rates in chemical reaction. And then we can look at, so here is an example out of a scientific paper, and I will simply leave the reference to Taylor. This is the doubling cascade in convection of mercury in a small convection cell. So the cell, they show the temperature as a function of time for a fixed point for successively larger temperature gradients. So what you see there, you're applying a temperature gradient, and you're seeing that the actual that the convection rates are changing. So totally different system, but you still see the same doubling cascade where this Rayleigh number is measuring the convection. So the phenomenon occurs in many different systems and is called universality. What you see is that the number of doublings increases with the increasing gamma here. So the doubling begins to occur, if you look at the solutions that we did so far, it begins to occur between a gamma somewhere between 1.06 and 1.078. Numerically, it would be hard to, if you were just solving these systems by guessing, it would be hard to figure out where it does, where this doubling sets in. For this particular system, the doubling sets in at a threshold of gamma of 1.0663. And at that point, you start to see doublings. And you can look at the intervals between the thresholds for each doubling, and it will roughly follow something like this. The difference between the spacing between the doublings goes like 1 over delta gamma n minus gamma n minus 1. And this number here, delta, turns out to be 4.6692016. This is the Feigenbaum number. And this phenomenon of doubling cascades has been characterized as universal. What happens is that gamma will approach some critical gamma as n goes to infinity. So gamma 1 is less than, and gamma 2 is less than gamma 3, and so on. And for the damped driven pendulum, this critical gamma turns out to be 1.0829. Beyond this, so you're going to get doubling cascades as long as you're below that, and beyond that, chaos sets in. The period doubling cascade is called the route to chaos, so we have not quite made it to chaos when you have the period doubling. You still have some predictability in your behavior, so it's not yet chaos. These are the systems. There are systems which lead to chaos without the doubling cascade, but this is just one of the several routes to chaos. So then we can look at chaos and the sensitivity to initial conditions. So here you can see figure 12.10. The system, here we've got gamma of 1.105, so that's above our critical value. You can see that the system is trying to oscillate with the drive frequency, but it isn't succeeding. In some ways, it almost looks periodic, but it's not quite periodic. It's never, there are, if you were to divide by a function like your best fit of this function, you would see there are deviations and they don't follow a pattern. So here we can start to quantify the sensitivity. We want to quantify the sensitivity to the initial conditions. So we're going to imagine that we have two different pendula with two different solutions, phi 1 and phi 2. And they each have different initial conditions. We're going to quantify how they differ as a function of time, as simply the difference between the two solutions. So for the linear solution, this is going to go to 0 as t goes to infinity. So we had this envelope of this exponentially decaying envelope driven by the damping, which made the homogeneous solution go away, and you ended up moving towards the particular solution. So as time went on, you ended up with the same solution regardless, because you ended up all on the same attractor. When we were below chaos, when we had a driving force which was not quite strong enough to push us into chaos, but it was above what would lead us to a nice, neat attractor, we had this solution. So phi of t, we have our attractor. And then I'm actually going to write it as e to the negative beta. Now, in principle, you could have any of the other possible solutions. Because we're considering when you do have damping, you don't have undamped motion, but you could have overdamped motion instead of, or critically damped motion instead of underdamped. But mostly we're talking about underdamped. And these guys are going to be set by the initial conditions, but you still would end up moving towards this attractor. So if you're in that underdamped phase, your difference in the angles of two different pendula with different initial conditions is going to go like some constant e to the negative beta t, and then you can always write this as the difference, the sum of cosines and sines can always be written as a cosine. The frequency will be the same, but you could have some different phase shift. And we're going to quantify this. So here, this is numerically what you would see. This is a drive strength of 0.1, so you were well below chaos. And then what you see, and this is on a log scale, so what we're going to do is take the log of both sides. We're going to plot it on a log scale so that you can actually see the differences, because this is going to die away rather quickly. So the log of the difference is some constant minus beta t plus here I'm taking the natural log. The plot shows the log base 10, which just shifts the scale, but log base 10 is easier to interpret in our heads because we work with base 10 numbers. So what you see is that the success, now there's some oscillations because you do still have oscillations with the drive frequency. So then what you see is that the amplitude of the difference, if you look at the maximum, this amplitude is decreasing. This is decreasing linearly. That's driven by this term. And this is solved numerically, whereas this is our analytical approximation of what the solution should look like in that case. So practically, your real initial conditions can vary slightly when you're doing a measurement. You don't know exactly what something is, so the real thing you started with might be slightly different. And if you are in this weak damped case, you are relatively insensitive to those slight differences, because either way, you're going to end up approaching the same attractor. You're going to end up with the particular solution in the long run anyways. But if you increase the drive strength but still keep it below this critical drive strength where you end up with chaos, you will, so you're still going to see exponential decay, but the decay is slower. So here you can see the gamma is 1.07, so it's above what we would call, it's above the threshold where we have are in our nice neat regime and we can solve everything, but it is below the threshold for chaos, and you see that it decreases, but it doesn't decrease as fast. So here it's a log scale. Here you can see that over about 40 periods it decreases by about 5 orders of magnitude, whereas if we toggle back here, over 10 periods, it decreased by 12 orders of magnitude. So this is dying down, but it's not dying down nearly as quickly. And here, this is a fascinating plot. What we've done here is that we have gamma of 1.05. Wait a minute, gamma of, I have skipped one. Yeah, sorry, this is gamma of 1.05, and the difference with a pendulum that is only different by 10 to the negative 4 radians, so very slight differences. And what you see here is that this difference is actually increasing and not decreasing. The two pendulas start out moving in very similar, in a very similar trajectory, but their differences grow. So long-term predictions in this scenario, where the gamma is above that critical gamma, become impossible. So then we can try to, when we can look at higher values. So here you see a gamma of 1.13, and you see that the difference does not, in fact, the difference settles. So here, this guy has settled down to an oscillation with a period 3, and here you're in the period 3 region, so the differences do die down somewhat, but only because you're actually in one of those special regions. And then here we can move further. This is a gamma of 1.503, and you see this is where we're starting to see some chaotic motion. So initially the difference decreases, and this is now on a linear scale, not a logarithmic scale, but then you start to see the differences increase. So it actually changes whether or not they're getting closer. So this is the phi, the delta, this is phi versus TPT, and this is the log of the delta phi. So the differences oscillate, or the differences start growing eventually. So then you can try to quantify this. And how do we want to quantify this? You can describe that difference. We want to take the absolute value because we don't actually care whether it's above or below, as e to the gamma t. And this number lambda, e to the lambda t, lambda is called the Lyapunov exponent. So where this is less than 0, you have non-chaotic motion, and it settles down to some periodic motion and oscillation, and then where it is greater than 0, you have chaotic motion. So this was in our narrow window of our narrow window of convergence to neighboring solutions, because we were at period 3. So if you have a system that a gamma where it wants to be at period 3, the solutions will go there. It's an attractor. But then you go higher, and they get further apart, and then they get closer together. And this is it returns to the chaotic motion when you're no longer in that region. So it is so here you can see approximately steady rotation of 1 revolution per cycle with some erratic jumping back and forth. So once the drive strength is above that critical value, there's a region where it is chaotic and a region where it is not. And the chaos can take several forms. It can take erratic jumps like this. Erratic in the case of the pendulum, it can be erratic rolling motion. It doesn't necessarily follow a trend. And the erratic motion goes with a sensitivity to the initial conditions. Now, we want some way of quantifying this and understanding it, so we're going to look at something so we've described that there's regions where you have relatively predictable behavior. It might technically not be totally periodic, but it's approximately periodic, and then you see these regions where you have period doubling, and it's you have more than one attractor, you have two. You may have two, but you at least have a solution. You can tell me in that region roughly what the system's going to look like, and then you have these periods of chaos, and at some point you get to a region where you have only chaos. And yes, this is showing where you can get to, you might have, depending on your initial conditions, these are the 2 different angular positions, you can have 2 different attractors. So then we want a way to quantify this. So this is phi as a function of gamma. And this is called a bifurcation diagram. And what we're going to do is that we've got some motion so it's being driven in a periodic fashion. So this may be our driving force. Actually, let me make more periods. And we're going to plot the the phi for multiples of that period. So let me do a driving force. And now we're going to have some solution. So when we have our nice, neat solution, I'm trying to draw something. So here, this is semi-periodic with the chaos of my own drawing added on top of it. So, and this is going to be phi. Let me actually draw it in the same color. So I'm gonna draw the point at every period. So here, let's say I start here, and this is tau, the period, and then so this is 1 tau, this is 2 tau. I'm gonna have 3 tau and 4 tau. And I can do this numerically. We live in an era where I can kind of throw numbers at a computer, and I'm not that limited by CPU. So I'm going to take, for a given set of initial conditions and a given gamma, I'm going to draw the phi at every period after that. So tau, 2 tau, 3 tau, 4 tau. And I'm going to put a dot on the plot. And I'm going to wait a little bit to see if the system equals out, so I'm not that sensitive to any funny business at the beginning from the homogeneous solution, from any of these transient solutions. So here I've actually shifted the x-axis. This is at like maybe 10 periods, and then I'm going to see where those numbers are. So if I am in a region where I have basically periodic motion, even if it's not exactly my nice, neat, simple harmonic oscillator with weak driving, with weak damping, I'm going to see that it's periodic, so it always reaches the same time. So however many dots I draw for a specific point gamma, as long as, because I'm always going to my attractor that has this form, I'm always going to the same attractor. So after a long enough time, it'll be, because it's going to be periodic, it's going to be at the same point. And at some point, when I crank gamma up a little bit more, this is where I start to see this period doubling. I push gamma just a little bit further, and it will have a different shape, but I'll have one of 2 points, because I'm either going to be above, I'm either going to be on the first period or the second period. I'm going to have 2 possible heights. And if I'm going to flip back to one of these, let me flip that back to one of those. Here, if I'm in this region, I'm either going to be at this phi right here, or I'm going to be at that phi, depending on which phase in the cycle I am. So if I'm plotting every single one of those, I'm going to hit one of 2 values. So here, if I can get back to the diagram I wanted, here, that's where I see my doubling, and I have a long region on this plot of doubling, and at some point, I have quadrupling, and you can even see, and the book talks about this in extensive detail, the different patterns that you have where you double, and you have this equation with the Feigenbaum number to tell you where it starts doubling. So this part here, we call this bifurcation. That's why it's called a bifurcation diagram. It shows you when you split into this doubling. In this region here, the period is tau. The period is the driving frequency. In this period, the period is 2 times tau. And here, so here you have another doubling. And then over here, you have, at some point, you go above the critical value, and your points, wherever they are, they're always, you're never getting periodic motion. This is the chaotic region. So there is some point where there's one point here, this is where you have those regions where you have anomalous periodic motion if you're at just the right driving force. And this can miss. So this shows you qualitatively the behavior of the system. This can miss some patterns in rolling because, of course, we're talking about something moving and its motion is cyclical. So if you're watching, assuming that you don't have like a cord that can get wrapped around and get the whole thing stuck, you can't tell the difference between something being at pi, let's see, that's pi over 2, or 5 pi over 2. They look the same to you because this externally looks the same if you have no idea where you started. So this is the same diagram, except what we have done here is now phi, let's see, this is phi dot, and here this shows, so A to B across F, this is the, so A is the same thing that was shown in greater detail here. And you notice here, look, this scale goes up to 1.5, and this guy went to 1.085. So this whole thing right here is now crunched in here. And then this mostly starts with a period 1, followed by the doubling cascade, leading to chaos. This region B here, this is mostly chaos. C has a period 3, so you see that we're jumping to period 3. And then this is mostly chaos, although you can still see that you have an almost period 3 type motion here. And then here you have a region where you have period, let's see, D, yeah, then you have this region which is mostly, which is period 1, followed by another doubling cascade, followed by mostly chaos. And here we've looked at phi dot because it isn't really impacted by that ambiguity in phi. And you will still see still see the periodic motion, and you're just going to change the amplitude of the rotation. So this plotting versus phi dot is going to work even with rotation, even with this rolling where it goes and it goes further and further. And then here we can see, so this is phi, this is the same pendulum, and this is just showing one set of values. This is phi, where you can see that rolling motion. Phi is constantly changing, but when you plot it versus phi dot, you start to see the periodic motion. So we want to talk about how we quantify this in a different way. So the problem here is always that what we have done before we hit this chapter largely involved things that are predictable and nice and neat, and we know where they're going, and we can draw them on a plot with a single line for a function. And now we're talking about chaos. How do you quantify chaos? How do you work with chaos? So we are going to talk about something called a Poincaré section. So we want to write, we want to follow both the position and the velocity. So we're going to consider this our the plots that we're looking at. And we're going to look at the phase space trajectory. Now, this book uses the term state space more often. I have much more frequently heard phase space, which is where something is. So when we talk about phase space, we're often talking about, where, position and velocity. We're talking about where in all of the motion this is. And we can go with an example. Let's first start with, here you can see a conventional plot. This is phi as a function of time. We start at phi of 0 is negative pi over 2, and the initial velocity is 0. And this we can map onto here. So we take this plot, and if you took this plot for phi as a function of time, you could write phi dot as a function of time. And here I have phi on the x-axis and phi dot on the y-axis. I start out at phi of pi over 2, and then I have and actually I think that should be a negative. Indeed, it doesn't show up very clearly, but this is a negative pi over 2, and it starts out with a velocity of 0, and then you can follow it. It follows a trajectory as a function of time. So we're not putting time on the x-axis. We're asking where in phase space is it, what phi dot. And you see it circle in, and this first plot is showing the first 20 cycles, and you see that after a while it approaches the attractor. This one shows cycles 5 through 15, and you can see that at least within the numerical precision, they're all following the final attractor. So this is called a Poincaré plot. So here, and here you can see this plots out, at least for the damped driven pendulum. It makes an ellipse. It makes an ellipse because it's oscillating in this direction and in that direction, and they each have different, they in principle at least can have different amplitudes. Of course, they also have different units on this axis and that axis. So then here is a different plot. So this is showing you start here with zero velocity and an initial velocity of 0 and initial position of 0. You're driving at the drive frequency, and you are going to approach the attractor, and this shows the last 10 periods. Again, here the time is always in units of periods. So whenever it says 5, it is 5, this is from 0 to 20 periods. And, excuse me, so the state space is defined by phi and phi dot. The configuration space, which is what we are used to, is just phi. And in general, configuration space is if configuration space is n-dimensional, so we would talk for any given system, it would be the Qn, the variables that describe the position. The phase space has dimension 2n because you have velocities for each of those. And this then has dimensions 2n for the state space. And it defines the motion is defined exactly if you have the velocity and the position. And it also tells you the initial conditions. And this path, this is so the space state orbit is the path traced by the pair of velocity and of position and velocity. And it says that there is only one state space at a given time. So here we have one pendulum. It has one position, one velocity. And then you can have, so here, this particular plot, so this is in the region where you have the period doubling. So when you have phi, you actually, so here you will go through one and the other. And if you, this is in the period 4 region, you will actually see that there's 4 different lines. And this is tracing out cycles 20 to 60. So you've already reached your attractor, but because you're in period 2, you have 2 different ellipses, and at some point they cross, and here you're in period 4. So you have 4 different, well, I guess I should call them, they're not quite ellipses. Let me call them ellipsoids. They're sort of ellipsish. And when you get to, this is in the chaos region. So here you haven't yet, so here this is gamma of 1.105. So you are, here it is moving. This is the first several cycles, 14 to 21. And then here, this is 186 cycles from 14 to 200. So it causes, it's semi-chaotic. You don't ever reach this region of phase space. You don't ever have 0. You're never at 0, 0. Of course, you're in the region where you're being, this pendulum is being driven by a force, so you're not going to reach 0. But this is in your region where it's semi-chaotic. Um, and then the question becomes how to extract useful information. So, of course, here, I think earlier I had said these are a Poincaré section. They are not. These are the state space diagrams. So, of course, we've got rolling motion, and this already came up earlier. Your motion might actually, when you have the rolling motion, this might not be so useful because if you plot it on a plot like this, well, you would end up having to create, you'd have to expand your axis range, and it's going to muddy the waters because there's actually not really a big difference between an angle of pi and an angle of 3 pi. So we can make these state space, so you can take a system like this where it's rolling, so the phi covers a rather large range, but the phi dot, the velocity, doesn't actually cover that much range. And you can make the state space diagram and wrap phi around. Now this comes at the cost, so we call this a map. So this has jumps because what you see here is that every time you reach this point, you wrap around and start at the beginning, but then you can see the semi-periodic motion that doesn't show up if you were to simply stretch out your x-axis a lot. So the discontinuity is spurious. You can imagine this pasted onto a cylinder if you were able to draw a cylindrical graph. So it's not actually jumping, you're just wrapping around to the beginning. And then here, this is the state space orbit for the chaotic region. So here you've got a gamma of 1.5 and beta of omega naught over 8, 190 cycles. It does not repeat itself in the regions shown, and in fact, it never repeats itself. So this is showing you something, but it's not giving you a lot to quantify the motion. You want to know how you can quantify the motion. So what we're going to do is look at something called a Poincaré section. So Frenchman Henri Poincaré. You are going to, the state space orbit is just too full of information, and it's not actually full of useful information. So you end up being distracted by the sheer volume of information. What we're going to do instead is that we're going to actually take a trick from earlier. We're going to plot points only at a given time. So we'll start at some period T naught, and then we're just going to plot we're going to look at the system at multiples of that period, so that we reduce the amount of information that we're trying to look at. And we're going to go, T naught's going to be large enough that we're not really worried about the transient solutions. And here you can see your state space orbit looks like this. But now we're going to look at these points, and we're going to plot one point for every repeating period. So where the points fall depends somewhat on what I set T naught to. But if you look here, since this is at a point when the motion is in fact periodic, when I repeat this, so if I pick times after multiples of tau, and I take these 2 points, T naught and then 2 pi plus T naught, I'm going to have 2 points that I can possibly be in phase space. So it significantly reduces the amount of motion. So when the motion is periodic, you'll see just a couple points where your system will fall, and there's no particular advantage to a Poincare section. But when the motion is not periodic, that's when you see an advantage. So here you can see an example of a Poincare section, and for a particular set of our initial conditions. And what's interesting here is that you see that the pendulum never quite reaches certain regions. And here you can zoom in. You see that you see similar shapes, and you can take this and zoom in further. And every region of the diagram, you zoom in, it looks similar. And this turns out to be something called a fractal, that wherever you look, when you have this chaotic motion, the pattern looks similar in different parts of the diagram. And this is, I love this. Sometimes Taylor just gives these lovely quotes where you go, yeah, so this is a direct quote out of Taylor. Although it is certainly not obvious exactly what this elegant figure signifies, it is certainly obvious that it signifies something. So this is a fractal. When it is enlarged, it looks, or zoomed in, it looks like the original picture. All right, so we're going to move on to discussion of discrete times and the logistical map. So you often have, so far we've been talking about things with continuous time, and what we're going to develop is actually a slight deviation from the damped driven pendulum, and talk in more general about discrete times. Now, sometimes we've treated the pendulum as discrete anyhow, because we have broken it down and said, well, we're just going to look at 1 times the period. Because if we do that, it's giving us all the information that we need. Now, there are a lot of systems with discrete time, or where you may only need or be interested in data from a discrete time. So the timing of the Super Bowl is discrete. There's only 1 per year. But you can also look at things like the population of a specific type of bug every year. You may only look at spring or in winter, but you're broadly going to learn information about that population, even if you don't have the bug population over the whole time. So sometimes we are only interested in discrete measures of continuous systems. And the Poincare diagrams sections reduce continuous systems to discrete functions, but there are other functions where it's discrete inherently. So we're going to start by considering cases where there is a function. If we have phi as a function of t, so where we get phi of t and phi dot. If we want 1 step further, we can describe that as a function of the previous pair of points. And we can write this as the value of something at time t plus 1 is equal to some function of the value of that thing at time t. And this is called the growth equation. So for example, we can consider exponential growth. This is example 12.1. In exponential growth, the population at time, well, we're considering t plus 1, we're thinking 1 period. It could be 1 year. It could be 36 seconds if your period is 36 seconds. So we'll call it t plus 1. We really mean t plus tau. You can always change your units so that your units of time are 1 period. This is some function of n at time t. And for exponential growth, we are going to assume some constant times nt. This constant is the growth rate of the population. So n1 is r n naught, n2 is r squared n naught, n3 is r3 n naught, and t is r to the t n naught. So if r is less than 1, the population decreases exponentially. If r is greater than 1, the population increases exponentially. And if r is if r is 1, then the population stays constant. In math, in mathematics departments, the term function is synonymous with map, so we will sometimes call this a map, because you are mapping n of t to n of t plus 1 using f. And we say that nt maps to nt plus 1 through f. And so on. This is an iterated map because it is discrete. We are going to shorten that and call it map. And we're going to talk about a map for a discrete function. This particular one is a one-dimensional map because you are mapping one variable onto the other. In this case, you are mapping, you are only mapping one variable as a function of time. In this case, you're mapping the population at one time onto the population at a later time. The Poincaré section is a 2D map because you have both the phi and the phi dot. And we are going to study in greater detail something called the logistic map. In the logistic map, this is a variation on exponential growth. It actually comes up a lot in studies of biological systems because it is a reasonable approximation of a lot of biological systems. So in this map, f of n is Rn 1 minus n over some maximum n. N is the population, and then that would tell us that the population at time t plus 1 is the function of the population at t, which is r nt 1 minus nt n. And I should say, I said that this is a good approximation of biological systems. This is a good toy model of biological systems. It often tells you some qualitative features. So when you have a small population, so nt is much less than n, than capital N, then this roughly looks like exponential growth. When you have a large population, let's say that nt is greater than n, then you're going to have a die-off. Lots of your population dies because you're, you have to have n less than this because if you can't have a negative population. So you only have meaningful values of nt if nt is less than capital N. But if you get pretty high, the population is going to start dying off. And if you have a population of exactly n, your population is going to die off because the next year you're going to have a zero population. This n is called the carrying capacity, and its behavior, the behavior of this function is nonlinear. So here you can see the difference between the exponential growth and the logistic equation. So here you see that with exponential growth, the beginning, both of these have an R of 2, but this one has a carrying capacity of 1,000, and you see it levels off at 500. Then here you can see exponential and logarithmic growth. Exponential and logistic growth, but both have R equals 2, and exponential increases, whereas that one was the one that leveled off at 500. And then, this shows you start at different initial values. So in here you have R equals 0.8. When you have R equals 0.8, this is the region where your population is always going to decline. So in this region, the population dies off, and it eventually, because each time your population is going to decrease, so you approach 0. This shows the logistic map if you have an R of 1.5 at an R of 1.5, then the population, if it starts above the maximum, it's going to level off. If it starts below, it's going to approach the stable point. I should mention, I forgot one thing, that in the interim between these figures, the variable x was defined, which is the population divided by the carrying capacity. And if x is between 0 and, you have to keep x between 0 and 1, you will never, an answer doesn't make sense if your population in the next round is negative. So x has to be greater than 0 and less than 1. And you will only get, I didn't mean to hit the button. You will only get you only get meaningful answers in this case if R is between 0 and 4. So here you've taken this takes different values of R. When R is small, the population dies off. And when R is above 1, it approaches some value. And this looks familiar. This is an attractor. So again, you're seeing some of the same behavior that we saw with the damped driven pendulum, but now we're seeing it in a completely different situation that we've kind of made up ad hoc, but is a pretty good descriptor, a pretty good toy model of biological systems. Okay, so here we say this is an attractor. And then we want to talk about special points. So are there, because these systems can have attractors, but we want to know if those attractors are stable or unstable. So at any point when you have a function, so you have your map, which tells you what your next value is going to be. And so we're going to choose fixed points, and we're going to use the star to indicate that you have a fixed point. If your map, if f of star is f star, then this is a fixed point, meaning that if you ever reach this point, you're going to stay on that point. But then we want to know, is it stable? And this will sound similar to some of the concepts that you would have heard in a calculus class and in some of your other physics classes. So we want to know, we also call these equilibrium points. We want to know if it's stable. If you get a little bit off, is it going to return to this point, or is it unstable? If you're a little bit off, does it go elsewhere? So we can take our map and solve it for fixed points. If we do that for our logistic equation is, our logistic map is this. So what we're going to do is solve when this is equal to x, And those are going to give us our fixed points. This happens to have the solution, x equals 0, and we'll call it star because that's our fixed point, r minus 1 over r. And then we want to investigate the behavior around those fixed points. So here, this line right here is x, and this is our map, f of x, and when the two are equal, this is where we have our fixed points. So here we've got f of x plotted for r greater than 1, and you see that it arcs above x, so you will get two fixed points, one at 0 and one above 0. This is r less than 1, and here you see that there is in fact only one fixed point. And when you look at our solutions, this point is at r minus 1 over r. So for some values, you're only going to have that if r is less than 0, and that doesn't make physical sense. And our other point is right there. So you can see that at some point you move from having one fixed point to having two fixed points. And we're going to take this problem of the logistic equation and we're going to analyze what happens. The reason we're going to do this is that it actually we can take the same techniques and apply them to other systems. And you'll see that a lot of this discussion mirrors the discussion that we were having around the damp-driven pendulum, because both of them are systems that can act chaotically. So what you can see is whenever you have this map that has an arch downward, you're going to have more than one fixed point as long as it goes above x. What we want is a test for stability. So here, this tells us how many points we have. How do we test for stability? What we want is, if a fixed point is an attractor, we need to know if it is also a stable point. Well, a fixed point is an attractor if it is a stable point. It is not an attractor, it's actually a repeller if it is unstable. So let's presume that x of t is near some attractor. Epsilon is just a small number, we'll call it epsilon sub t. So x of t plus 1 is f of t, which is f of x star plus epsilon t, which is going to be approximately f of x star plus f prime of x star times epsilon t. Now this, because we have a fixed point, so f of x is equal to x. So this has got to just be x. Those are the same colored marker. All right, this is just going to be x plus, and then we're going to call this lambda epsilon t. And this has to be x star plus epsilon t plus 1, because this map has to also work for moving from here to here. So here I just used calculus. Here I used my definition of a fixed point. And now here I've got to be close to the fixed point. I'm assuming that I can have small epsilons. So then lambda is going to be our derivative evaluated at the fixed point. And we call lambda the multiple or eigenvalue of the fixed point, because every time you act on it with the function, you're going to be, that's how much you change your mapping. So if lambda is less than 1, then this approaches the attractor, because if lambda is less than 1, every time, then in the next iteration, you're going to be even closer to x, because in the next iteration, this is going to be less, this term is going to be greater than that term. You get closer to x star. So we have our condition for stability of fixed points. If our derivative, and it actually doesn't really matter if it is positive or negative, the value has to be less than 1. So you could oscillate back and forth as long as the difference between x star and as long as the difference between x star and your point is decreasing. So if this is true, you have an attractor. And if this is not true, if f of x star is greater than 1, your point will repel solutions. All right, so then we can look at what this does for the logistic equation. And for the logistic equation, we have f equals r x 1 minus x, which means f prime of x is r 1 minus 2x. So for x star equals 0, f prime x star equals r. So this is stable if r is less than 1. Now in that case, the attractor is x0, the population is going to die off if your growth rate is less than 1. That kind of makes sense. For our other attractor, x star is r minus 1 over r, and f prime of x star is 2 minus r. Now, we cannot have r less than 0, so because we cannot have a negative population. So now if we get r, so here, this one's stable until r equals 1, and then this guy is stable for r equals 1 to r equals 3, and then it is, because I have to have this less than 1, and then, so I can change this by 1, but not by more. And it is unstable if r is greater than 3. Now I want to note, this point did not even, this fixed point did not even appear until r equals 1. So we don't have any we only have the one fixed point until r is equal to 1, and then when we have 2 fixed points, this is stable for r equals 1 to 3, whereas this one becomes unstable. Here we can take that and plot this. So this shows our fixed points, so here the fixed point is stable, where this is x star and this is r, and it is stable from 0 to 1, but we only have 1 at x equals 0. At r equals 1, we get 2 fixed points, and the one at r equals 0 is unstable, and the one at the one given by the curve is this one is stable until we hit r equals 3, at which point it becomes unstable. Instability here is denoted by a dashed line. And then we can look at the behavior that happens after r equals 3. So here, this is an r of 3.2, and this is, because it's numerical and it's discrete, you can just plot the values. So this is for a small initial x, and then what you see is that the x's start to oscillate. And this is actually rather similar to the behavior we saw with the damped-driven pendulum, and they start to oscillate every other cycle. And neither of these then, at this point, neither this point, you can see that it is kind of, well, it kind of looks like it's attracting points, but neither of them is a fixed point. So then we can look at the double map, because what it looks like it's doing is it looks like it's oscillating between two different points. So you can define a function g, which is the map of x. So x of t plus 2 is then g of x of t. So we're doing it twice. And we will have a fixed point if x of a is a fixed point, if g of a is x of a, and the same thing for g of b. So the two cycles of f, that's what these are called, are fixed points which are not fixed points of g, which are not fixed points of f. So if there are numbers for which applying f twice leads you to the number you started with, then this would be a fixed point of g, but it is not a fixed point of f. So this is a way that you can get more fixed points. And the 2 cycle appears when the 1 cycle becomes unstable. So here, at the point that the first point was unstable, you get 2 possible stable points. And it occurs when g prime of x, when it occurs for the values where the double map is equal to x. And here in the book has a lot of words about this. So this is the single map, this is the double map. So here, what you will see is that for r's that are greater than 2, this is an r is still less than 2 here. So here, r is less than 1. You only have 1 fixed point. The double map is not bringing you to stability. It's not bringing you that second fixed point. R is still less than 2 or less than 3 there, so you don't yet have you don't yet have more stable points. But then we can look here, r of 2.8. So the solid line is f, the dashed line is g. This is r exactly equal to 3.0, and you see that this line begins to become tangent to x equals to the function x. And then when you go slightly above it, your double map dips below x, goes slightly above, and comes back down. And so the double map actually has those 3 stable points. So then you can look at this, and there's a little bit of calculus you can do, and you will get that the 2 cycles appear when f star, or the squared, is equal to 1. And you can take this and plot it as well on a bifurcation diagram, just like we did with the damped driven pendulum, and this shows you the stable points as a function of r. Now this is discrete points, so you actually can begin to write them. And we can do this numerically. This is the bifurcation diagram for the logistic equation, and here you see this is as a function of r. So here you see, you see your fixed point, and then here you see the doubling, and here you see your 4 cycle, you see periods of stability, and it very much looks the same. And you also can see here that there are regions which have periodic behavior sandwiched between regions of chaos, which is just like what we saw earlier. And this is a good place to end, to say that you see the same types of trends in the different approaches to chaos.